Okay, let's welcome our first presenter, Mr. Rulian Barros from the University of Mississippi. The topic of his presentation is performance prediction model for flexible payment in Mississippi using neural networks. Okay, Mr. Barros, could you please share your screen? Okay, thank you.
Okay. Just 1 second. So let me share. One minute. Okay, everybody can see my screen?
Yes.
Okay. Good morning, everybody. So I'm Rulian Barros from the University of Mississippi, and I'm here to present a paper on performance prediction models for flexible payments in Mississippi using neural networks. I'm Rulian Barros, and the other authors are Dr. Hakan Yasser and Dr. Salma Sultan. So let me start giving a brief background of this research. So to assess the pavement surface conditions and ride quality, two of the most widely used measures are the performance condition rating, PCR, and the International Roughness Index, IRI. And transportation agencies are required to maintain their pavement sections at acceptable quality levels for the safety and comfort of the road users. For these reasons, the pavement performance models that are capable to predict pavement conditions and rehabilitation needs are crucial in the pavement management system. The objectives of this paper are to analyze roughness data for flexible pavements in Mississippi, develop the pavement performance models using the artificial neural networks approach, and to perform a sensitivity analysis for a random section of the database. This is the methodology used in this study. So first of all, we need to gather all the MDOT database. In this study, a flexible database was used. So data processing for cleansing these data only for asphalt pavements were necessary. And then processing this data into a modeling format, and it starts a data visualization process using geospatial maps, creating correlation plots, and doing statistical analysis. After this, a further investigation of the input and output variables was just started to start the pavement performance model development. This pavement performance model development used a machine learning technique. To use the machine learning, an artificial neural network was chosen as this technique. And in this study, a dynamic sequential artificial neural network was used. Talking about the artificial neural network, what it is and what does the artificial neural network does. So it used the concept of the human cognition and neurobiology and obtains knowledge through a trained feed-forward network. So we feed the data, we train the models, and we get the model as at an optimum network. So how it does, the output is compared to a target value, and a backpropagation algorithm adjusts the connection weights to reduce the error. And we do this several times in order that we can minimize the error and optimize our result. In this ANN network, activation function using a sigmoidal function, which is one of the most used functions to introduce the non-linearity in the model development. So by doing this, the model will get the non-linearity behavior and can predict better values depending on how the complex relationship between independent and dependent variables are. This is a simple ANN network construction. So we have the input layers is the first layer. So you can input your variables. Then you have connections to the next hidden layer. These connection weights, they are adjusted according to the target value when compared. So after the hidden layers, you go to the output value that is then compared to a target value, comes back with a back propagation, and starts again until you reduce the error to get your optimum values, your optimum prediction. In this study, this dynamic sequential approach that was used to characterize the continuous data response. This approach is used when you have a time-dependent data. So for these pavement performance models, we have a time-dependent that goes year by year, and in a sequence that you have equal time periods. So what is the difference between this dynamic sequential approach? You can see that it follows the same approach as the normal networks, the normal ANNs, but after you get the output, this output comes back as an input for the next prediction. By doing this, you can improve the predictions when you have a time-dependent data. Several studies show that this type of ANN technique has better predictions than the normal static ANN networks. The ANN model development in my study used 4 stages. So stage 1, first you need to determine the ANN architecture, decide what are the inputs and the output variables. After this, you need to classify your data set in 3 different data sets: training, testing, and validation. In my case, we use 50% for training, 25% for testing, and 25% for validation. In the stage 2, we train and test the network on the experimental data to obtain the optimum number of hidden nodes and iterations for the ANN architecture. The stage 3, you need to validate the best performing network from the previous stage using the validation database and check if the accuracy results from training, testing, and validations are comparable. So after this, you have the last stage, stage 4, when you retrain the best performing network from stage 2 using all experimental data. This you need to do to increase the prediction accuracy and account for all the patterns in your database. How was the data collection and processing for this paper? First, the database for this model development were obtained after cleansing and reorganizing the raw data files from MDOT. And the model used data collected from 2010 to 2020. So how MDOT collect this data? The MDOT collects this data in even years. So to develop the prediction models, we needed to have the odd years. How we did this? We generated these odd years by averaging the consecutive years from 2010 to 2020. By doing this, a total of almost 36,000 data points for almost 4,000 flexible pavement sections were used in the model development. And it was known in this study that MDOT did not keep track of all the rehabilitation actions. And for this reason, it was necessary to develop a new approach for assigning rehabilitation actions. And this was done discussing with MDOT and doing several researches on just the maintenance and rehabilitation, how we could incorporate this in our database. So what we did is that we created threshold values for the PCR and IRI and assigned them based on the evaluation of the data. How was done? We decided for a minor rehabilitation if the PCR increased 8 to 12% and IRI decreased 8 to 12%. A major rehabilitation was incorporated if PCR were above 12% and IRI were more dropped more than 12% from the previous years. Now, I'm going to talk about the model variables and the architecture of the 3 models that were developed for this study. The 3 models used 16 independent variables and 3 different variables for the dependent variables. Model 1, Model 1, 2, and 3, they are using the same independent variables. These independent variables were studied doing several other studies with different pavements and also to get the optimum number of independent variables. We came up with 16 independent variables that related to the location of these sections with beginning latitude and end of the latitude and beginning longitude and ending of the longitude. A structural number was also incorporated in this model, the length of the section, the age in 2010, since this was the first year of our data collection for PCR and IRI values, also in 2010. And we have a variable called time, which incorporates from 2010 to 2020. So we have time 1 to 9, 1, 2, 3, until 9. A drainage is a categorical variable that tells me if there were a drainage in this section or not. And the minor and major rehabilitation is a categorical variable that was used. For the traffic variable, ECL was included, the equivalent single axle load. And since I'm using the dynamic ANN, a pre-PCR and pre-IRI needs to be used in order to the output comes as an input for the next one. And for the dependent variables, that's what differs our 3 models. The first one, we use the complementary PCR. The second model used just the IRI mean. And the third model is a 2 output model with complementary PCR and IRI mean as a 2 outputs. So why we are using complementary PCR and not the PCR value? We know that PCR and IRI, they are inversely proposable. They have an inverse ratio. So every time PCR increase, the IRI decrease. For this reason, in the ANN model development, we need to these dependent variables to be directly proposed. So they need to be the same. When one increased, the other one also increased. When one decreased, the other one decreased. For this reason, this complementary PCR is 100 minus the PCR value. By doing this, we got better results. How we did the model selection? To do the model selection, they were based in 3 different statistical measures. So the best model was choosing as the one with the lowest average square error, the ASCE, the lowest mean absolute relative error, MER, and the highest coefficients of determination, R squared. Here is the first result using the model 1 and model 3 with the variable complementary PCR. We can see that from these results, training, testing, validation, and all data, model 3 outperformed model 1 with better results. But let's focus on the all data statistical, because using the all data is when the model is optimal and we are using all the experimental data that we have. We can see that MER for the model 3 was less than half of the MER for the model 1. And our R square, we have an R square, a high R square of 0.9 and a really low ASCE value, showing that model 3 was much more accurate than model 1. For the IRI variable, we have a different result, but also we see that model 3 outperformed model 2 with better R square, ASCE, and MER values also. However, these are, for the IRI model, we see that our R squared is not as high as we have for the complementary PCR. So this is our network for the best performing models. We can see that we have 16 input variables here. connected to 9 hidden nodes. These are all the connection weights to the hidden nodes. And then we connect to 2 outputs, since this is a 2 output model. For the ANN model results, we can see that model 3, when predicting PCR, we have a high R-square of 0.9, and we can see that all the points, they are really clustered around the line of equality, showing that the model could predict really well from the observed values. We can see that observed and predictor values are really close to the line of equality, which shows a really high accuracy. For the IRI model, we see a different behavior. When the values from IRI are from 0 to 2.5, they are close to this line of equality. But after the 2.5 meters per kilometer, we can see a different behavior from the data. So the model underpredicts these values, showing a value that is lower than what was observed. One of the reasons that this can happen is because we can tell that the behavior of a pavement with a high IRI is different from a pavement from a lower IRI. Because when you have a pavement that is not in a good shape, different types of distress, different types of problems happens in this pavement that the model could not predict. So maybe we need to develop 2 different models for lower and higher IRI values. But you can see that for PCR, we don't have this type of difference. The model could predict really well what happens with the pavement. The sensitivity analysis was performed in a random section of the database to see if the model was predicting well for one specific section, just to see how it performed. And we can see that for PCR, the predicted values are really close to the observed values, showing really accurate results from year 1 to year 9. And when we check for IRI, even if we don't have a really high R-square for the all data, when we got one section of the database, the predicted IRI from the model was really good. It overpredict the IRI values, but it followed the trend and the behavior of the pavement. So to conclude, we can say that in this paper, we successfully developed the performance prediction model for asphalt pavements in the Mississippi region from the MDOT database using the artificial neural network. Just to remember, this study was done just in the Mississippi region. And this should be stated because if we use sections from outside of this database, we cannot tell that the model will be as accurate as it was for the Mississippi region. The second conclusion that we can have from here is that model 3 with the 2 output model got the highest R-square for IRI and PCR. These 2 output model, when compared to the 1 output model for PCR, got a reduction of 77% for ASE and 49% for MER, and respectively improved in 47% the value of the R-square. For the IRI model, we got a reduction of 99% for ASE and 5% for MER, but the improvement of the R-square were around 19 to 20%, which shows that this 2 output model was much better than the 1 output model for this study. Also, the sensitivity analysis showed that the developed model was accurate when predicting both PCR and IRI for a random section of the database. Therefore, with this study, we can conclude that MDOT can use the developed model as a tool for predicting future conditions of their asphalt pavement, and then incorporate the MNR scheduling effectively to prioritize the resources. So they can use this model to predict when they need to do a maintenance and rehabilitation, if it needs to be a minor or a major, and then they can simulate several different scenarios to see which one of them will be the best option, and also prioritize the resources by seeing which section is in more need of rehabilitation. By doing this, they will save time money, and will be much more cost effective in their predictions. That's what I have for today, and I'm open to questions.
Thank you so much, Mr. Barros, for your excellent presentation. Does anyone have questions for Mr. Barros and his presentation? Let me see in the chat box. Is there any questions? So, yeah, if anyone have questions now, you can just unmute yourself and yeah, give questions.
Yes.
Mr. Barros.
Okay.
Anyone have questions?
I will leave my email here in the chat box. So if anyone wants to send an email with questions or, okay.
Oh, thank you. Yeah, Mr. Barros. Yeah, you can just type your email address in the box and make it visible to everyone. Yeah, make sure to everyone. And thank you again for your excellent presentation. And